Hello friends, so in this lecture we will look at some indoor reactions, the contrast with outdoors, some ozone-terpene reactions and the OH radicals. So why are these indoor air reactions important? Because in many places people can spend, as we have already seen, up to 90% of their time indoors. Mostly it is in homes, or this can also be while commuting commuting and in offices. So there is a wide range of gas phase reactions and also surface reactions, and at the same time the partitioning between gas and particle phases. So, and these reactions will eventually produce many complex and multifunctional products, and some of these products are also common outdoor pollutants as well. So there are a lot of pollutants which are common indoors and outdoors, and these are harmful for human health. So with increased energy efficiency in buildings, the buildings have become more airtight and the ventilation rates have decreased. So that means that if something is emitted, it is likely to stay, if something is emitted indoors, it is likely to stay indoors, and that would lead to higher concentrations, and any production or of course destruction of such kind of chemicals will also have implications on the human health. Okay, and so an interesting question would be, how is indoor air chemistry or the general setting of the indoor air different than the setting of the outdoor air? So first important part is the photolysis. So outside we can have sun, inside we are in a room, so anyways we have much less sunlight and much less direct sunlight coming in. So photolysis reactions are sometimes less important indoors because there is more shade indoors. The natural sunlight transfer is also low. However, there can be some important reaction close to windows. So sunlight can be important next to large sun oriented windows. So that means in an indoor environment, even in one single room, the indoor chemistry can differ by locations. If there is more shade in one location, those photolysis reactions will not happen. But when we are looking at a situation which is close to windows, the photolysis reactions will occur. So there is a difference in how much sunlight is coming in, but indoor has maybe less sunlight coming in, but there is other types of lights, like incandescent light will be there, LEDs might be there, fluorescent lights might be there. Sometimes people can also get artificial sunlight lamps. So the lighting within the room can also be different than outdoors. Outdoors we are mostly looking at sunlight, but indoors we can have some sunlight and we can also have light from different sources, LED, incandescent lamps, fluorescent bulbs and light sources, and also sometimes artificial sunlight sources. The other important difference is that in indoor environment we have much larger surface area which is available. Outdoor we can see, if we look outside, we have basically an open air situation, but in indoors we have tables, chairs, bottles, paper, all kinds of things are there. So indoor environment has a much larger surface area, and we look for walls are already giving a lot of areas. So once you consider all the wall, floor, coverings, furniture, then we know that the surface area available per unit volume of the room is high compared to outdoors, which means surface reactions become important, or the understanding of surface reactions becomes important. In outdoor environment, when the organic compound is oxidized, it may increase its water solubility, and when the water solubility increases, there is a higher chance that such a compound can be washed out by rain. It can maybe solubilize and partition more to the water droplets, and so when it rains it will be removed. But in indoor setting, if we do not have that much moisture as much as will cause rain, these products will not solubilize in water because there is less water available. So these oxidized products will accumulate in the indoor environment, and it may happen that these oxidized products are even more irritating to basically the nasal pathway or to human health than the initial organic compound, as these compounds have not been removed in our indoor setting. In outdoor they may have solubilized and settled, but now they do not have such an option, so they are probably going to be in the air more. Okay, and then there is, so that was the indoor versus outdoors. In indoors, the air exchange rates also influence reactions, because as we have seen before, depending on the air exchange rate, the compounds inside may be flushed out or new compounds will bring in. Now, so total time available for reaction is then controlled by the exchange rate of indoor air with outdoor air. So the reactions that can happen within the time period that the exchange is happening, they will be complete. Otherwise, if the reaction is very slow and much slower than the exchange rate, the compounds will be flushed out before they can react inside. For example, if my exchange rate is like 0.5 per hour and the reaction rate is only 0.05 per hour, it is 10 times slower than the air exchange rate. So the reaction will not proceed fast and the reactants will just be flushed out. Whereas if the air exchange rate is 0.5 per hour and the reaction time scale is say 20 per hour, so you can have 20 cycles compared to 0.5. So the reaction is much faster than the air exchange rate and is likely to proceed. Species especially which have primary indoor sources will decrease in concentration if the air exchange rate increases. So they are produced at certain rate, but then they are removed from the room. So the concentration, the influence on the concentration would be a decreasing influence. For species that have more outdoor sources, they will more come inside if the air exchange is higher. This slide summarizes some of the major reactions in indoor chemistry, namely NOx and ozone. Ozone, for example, can react with terpenes. We will look at terpenes in the next slides. And when they react with terpenes, we have secondary organic aerosol formation, then formation of carbonyls, carboxylic acids, peroxides, and some more radicals such as peroxy radicals and biradicals, which then may react with again VOCs and produce more secondary organic aerosols and other products. Ozone and NOx can react to form NO3 and OH radicals, which then again react with VOC to form secondary organic aerosols. Then ozone may react with the oils and terpenes on the surfaces, maybe humans or maybe some other coatings. And then again we have this production of similar species, SOS, carbonyls, carboxylic acids. NOx may react with surface, lead to formation of HONO, and through photolysis it can either form this radicals, NO3 and OH radicals, or from this tobacco smoke related nitrosamines. So basically these are some important chemical species which have implication on the indoor air quality, and generally all of them are going to lead to formation of possibly secondary organic aerosols or other pollutants and other chemicals as well. So, some of the key reaction types in the gas phase is focused on or has been focused on ozones and terpenes. In general, because these ozone-terpene reaction rates are fast enough to compete with the typical air exchange rates, and since these reactions are fast, they can influence the indoor air chemistry. So, ozone is a common pollutant indoors. The major source is generally the transport of outside air, and therefore our exchange rate is important because it determines the indoor ozone concentrations. When there are no sources of ozone, when there are no sources of ozone, the sources being photocopiers, laser printers, etc., the indoor ozone concentration is typically lower than the outdoor because of deposition or other reactions in indoor surfaces. And we have seen this in the lectures on indoor-outdoor relationships previously, that the ozone indoors is typically lower if there is no internal source of ozone, and the exchange rate is also not very high. Terpenes are some organic compounds. Generally, they contain a common building block called isoprene. Isoprene has this general formula C5H8, which is here. And terpenes have the formula of C5H8 to the power N, not to the power C5H8N. So, multiples of C5H8, the compounds which are multiples of this building blocks are terpenes. And the most common terpene is the monoterpene, which is N equal to 2. So, the formula is C10H18. Now, terpene species are natural products, and they are emitted in large quantities from vegetation, and they also have a quite a important impact on outdoor chemistry in areas where there are forests, for example, or a lot of vegetation. But in addition to outdoor sources, they are also quite prevalent indoors, and this is due to their emissions from sources which include timber, fragrances and cleaning products. In fact, so much that monoterpenes typically have concentrations 5 to 7 times higher than the outdoor concentration. So, the concentrations are much higher in indoors than outdoors, and they are even enhanced after cleaning activities are taking place. So, some more emissions happen, and the concentrations are generally in the ppb range. So, for typical indoor concentrations of 2 ppb limonene, which is a type of a stable monoterpene, and 20 ppb of ozone, the removal of limonene by ozone is equivalent to an air exchange rate of 0.4 air exchanges per hour. So, this is very comparable to the typical air exchange rates we have seen previously, which are generally 0.3, 0.5 per hour. Even if it is 1 per hour, the removal rate of limonene of 0.4 is still comparable. So, this reaction is competitive with exchange in many indoor environments. Additionally, these reactions also produce a range of short-lived products, and they will influence the ongoing chemistry together with the longer-lived species which are also produced from these reactions. How does it happen? Because ozone has an affinity for species that have a carbon-carbon double bond. So, here for example, so in the first step, the reaction between double bond species and ozone will happen, and it involves this formation of ozonide, which is the attachment of ozone to this carbon atom. So, here, and then one oxygen is combined with the other 2 oxygens. So, this is the formation of an ozonide. Ozonide species are generally energy rich and very unstable, so they will quickly disintegrate to form products. So, as an example, ozonide can form stable carbonyl products, which are like this, where R being an alkyl group, but it can also form intermediaries which are radicals, and these are known as Kriegi intermediate (CI). So that's the abbreviation, Ci species, which can then undergo further decomposition in the indoor air. So in regular atmospheric conditions, Ci species will generally decompose to yield OH, which is a hydroxyl radical, or could react with water vapor to form alpha hydroxy hydroperoxides, so a certain kind of peroxides. So here we have our Ci species. They will decompose to one species to another species, with the result being the production of a hydroxyl radical, or they will react with water vapor and form a hyperoxide, excuse me. So hyperoxide. Depending on what the parent species was, the alpha hydroxy hydroperoxide will remain as a stable gas phase species, or it can decompose to a carbonyl species, which is here. So this hydroperoxide is decomposing to a carbonyl species, and again another peroxide, hydrogen peroxide, or it will lead to the formation of carbonyl. So here now it is degrading and leading to the formation of carboxylic acid, COR, and some water. So that depends on what the actual molecule was and how are the energies of reaction. Here this is an illustration of squalene, in which squalene reacts with ozone to form a primary ozonide. So squalene is another kind of terpene, and then from this primary ozonide will decompose to carbonyl, as we have seen. But this carbonyl can react with more ozone and form aldehyde, and these aldehydes can nucleate or condense and form our secondary organic aerosols. That is one pathway of production of SOA. In another pathway, the ozonide decomposes to a Craigie intermediate, which undergoes isomerization to again aldehyde or carboxylic acid, which then nucleate or condense to form secondary organic aerosols. Finally, these Craigie intermediates can again form various decomposition, isomerization, and cross reaction products, which are similar like limonene ozonolysis case. So in general, all these reactions of terpenes, squalene being a triterpene, will lead to, in general, production of intermediates and end products, and production of secondary organic aerosols. So these reactions can lead a wide range of radical products such as aldehydes, peroxides, and then condensed phase species, which are quite important airway respiratory irritants. These are the rate coefficients for some of the monoterpenes with ozone, and so for the rate coefficient is in centimeter cube per molecule per second, and this is the ozone yield for the reaction. So ozone yields can range from 0.2 to up to 0.7, which is to 0.8, which is a non-trivial amount. And the other important thing is to see this ozone switch, which is the ozone indoor concentration for terpene to become a net source of OH radicals. So as we have seen, terpenes can essentially also lead to the formation of ozone radicals, OH radicals, and so ozone switch happens at the concentration of ozone in ppb, at which terpenes become a net source of OH radicals. As we have seen, the concentrations can be as high as 20 ppb in the previous slides, which means, with the exception of beta pinene, which is here, of whose ozone switch is 267 ppb, all the other species are likely to act as a OH radical source. Here ozone switch is 1 ppb, 4 ppb, 14, 23. So these are lower or comparable to the 20 ppb approximately mark. So all these compounds with the exception of this beta-penene can lead to production of OH radicals indoors. Generally, it is seen that monoterpene reaction with ozone are slow compared to the equivalent OH radical, which are faster. If you see these rate exponents 10 to power 15, 16, here it is 10 to power 10, 11. However, the indoor concentrations of ozone are very high than ozone concentrations, 5 to 6 orders of magnitude. So, although the reaction rate is 4 to 6 orders, so 10,000 to 1 million times faster, the concentration of ozone is 1 lakh to 1 million times higher. So, the higher concentrations are sort of compensating for the slower reaction rate, and therefore the reactions of ozone with monoterpenes become important, and so much so that actually for all these compounds except one, the ozone will react and form OH radical. We have already seen that the maximum and minimum yields can be 0.8 to 0.3, and depending on the individual rate coefficients in indoor ozone concentrations, monoterpenes can act as either sink or source of OH radicals indoors. We also saw that with the exception of beta-penene, the oxygen concentration required is within the range of what is observed indoors, which means most of the monoterpenes, or at least many of the monoterpenes, will act as a net OH radical source. This is important, this OH radical is important because it leads to other oxidation reactions in the indoor environment. The reactions of monoterpenes can also produce with ozone can also produce hydroperoxy and organic peroxy radicals, and sometimes very similar yields to the OH, and these can be transformed back to OH radicals. So, our HO2 can become OH either with reaction with ozone or reaction with NO. So, here we have reaction with ozone gives OH plus 2O2, HO2 plus NO will give OH plus NO2. Now, we move to the OH radical. So, it has been suggested through modeling works that OH should be present indoors. In fact, steady state OH concentrations were predicted to be around 1.2 to 1.7 10 into 10 to the power 5 molecules per centimeter cube. Some detailed chemical models predicted a maximum value of 4 into 10 to the power 5 molecules per centimeter cube. In general, models predicted that most of the OH radicals indoors will be formed through the reaction of ozone with monoterpene. So, again, this ozone plus monoterpene reaction is quite important for OH radical formation in the indoor environment. Many studies have reported the measurements of OH indoors under various conditions and found the measurements to be around 1.8 10 to power 6 molecule per centimeter cube, a little bit less than the modeling studies, but that study the modeling study and the observational study are often under different chemical conditions. And it was observed that the highest OH radical concentrations were in the periods when the room was in full sunlight and in the presence of substantial concentrations of actually nitrous acid. Reported OH radical concentrations in background conditions were in a university classroom was 6.5 into 10 to the power 5 molecules per centimeter cube. When they started surface cleaning, the concentration became 4 into 10 to power 6, and then when some air cleaning device was used, 2 into 10 to power 7 molecules per centimeter cube. So, as the cleaning activity started, and we saw previously that terpenes are often used in cleaning products, the concentration increased by almost 10 times to 100 times. In the same study, again HO2 concentrations were also likewise higher when the cleaning products were used. Here we see background concentration was 1.3 into 10 to the power 7 molecules per centimeter cube, and when the cleaning products were started to be used, they became 4 to 6 into 10 to the power 8 molecules per centimeter cube. So it basically informs us that as the cleaning products are used, basically terpenes are released and they react with ozone to form OH radicals. It was found that these background OH concentrations are actually only a factor of 10 less than outdoors during summers, and they are comparable to outdoors at night time and during daytime in winter. So in the summers, the OH radicals are also produced outdoors, and therefore the concentrations are higher outdoors than indoors. But as soon as we take out the sunlight away from outdoors during night time or during even daytime in winter, when the sun is not that shining, not that intense, or there may be more clouds, the OH concentrations indoors and outdoors become similar in magnitude. The enhanced indoor concentrations of OH generally can become then similar or even higher than those observed outdoors. So OH radical formation indoors is variable, outdoors is variable, and depending on the situation outside and indoors, OH can actually become as important or more important in terms of concentrations than outdoors. Once OH radicals are formed, they will form a range, they will react with NO2, NO and a lot of VOCs depending on what is the situation indoors. This OH radical, as we saw again, it is quite closely linked to the hydroperoxy radical through a number of radical to radical reactions. And these HO2 radicals, take part in homogeneous series, a part of homogeneous series known as peroxy radicals, where RO2, it can be H or alkyl group and acetyl group. So it is OH is quite closely linked to the hydroperoxy radicals, or in general the peroxy radicals. So when OH reacts with the volatile organic compounds, our peroxy RO2, which are the peroxy radicals, they are formed, and then they are subsequently propagated to the HO2 radicals. For example, we have an initiation step when the reaction is with methane. So OH radical reacts with methane in the presence of oxygen to form CH3O2 plus H2O. So we have a CH3 alkyl group, O2, CH3O2. So that's a peroxy right there, plus O2. In addition to HO2, OH oxidation of a hydrocarbon also produces aldehyde. So, and then the HO2 is radically propagated back to OH through the reaction with NO. So now the HO2 reacts with NO to form again hydroxy radicals. Simplest form of aldehyde, formaldehyde, can also act as a propagator between OH and HO2. So here we have a reaction of formaldehyde HCHO with OH radical in the presence of oxygen to form our peroxy radical CO and H2O. If the level of NO is low indoors, the radicals themselves, the OH radicals themselves, can react with each other to form peroxides, and for the HO2 self reaction, hydrogen peroxide will be formed. So HO2 plus HO2 gives H2O2 plus O2. And for the organic peroxides, reaction with HO2, other compounds are formed. So here we have HO2 plus RO2 will have ROOH. When CH3O2, this radical reacts with HO2, methyl hydroperoxide is formed. So another peroxide is formed. So we have our peroxy radical with the hydroperoxy radical combining, peroxy radical with hydroperoxy radical combining to form an organic peroxide. So this radical with this radical is causing the formation of methyl hydroperoxide. These peroxides finally can eventually be removed indoors by different deposition reactions, which then effectively removes the radicals from the overall oxidation cycle. In the presence of NOx, the major route of termination of the OH radical is reaction with NO2. Here, so we have OH plus NO2 plus a third body or third molecule which is very much present in excess and removes the excess energy from the reaction. And then we have OH radical plus NO2 giving the formation of HNO3, so nitric acid. HNO3 also deposits on indoor surfaces. So it basically first removes the OH radical and then it also removes the NOx, in this case NO2, from the overall indoor environment system, although the HNO3 itself may be having important health effects. Reactions of OH radical with VOCs are generally much faster than the rate they would deposit on indoor surfaces, and also much faster than they are exchanged with outdoor air, and both of which are negligible processes for OH indoors. So these are quite fast, and as we saw, they can lead to formation of secondary organic aerosols. So in summary, in this lecture we have seen the differences between indoor and outdoor chemistry. We have looked, or we have gained an overview of important indoor reactions, and then we have dwelled more into the ozone-terpene reaction, the OH radical. Now in the next lecture we will look at the reaction of other key species, for example our nitrate radical.